Okay, so that was the question, right? We did we used the formula and we got 0.1797. So about an 18% chance that that would happen. Okay. Like I said, doing these calculations, you don't need a special calculator. You don't need a graph calculator. You just need a scientific calculator. TI 30, the one that's $10 at Walmart or on Amazon. That one you can use. But since we have those, the 84s and 83s, I'm going to show you another way. Okay. So if you go to the next page, or 2 pages, in 2 pages, you have this. These are the directions. This is straight from your book. The directions on how to do binomial distribution. There's 2 types the calculator does. There's binom PDF and there's binom CDF. When do I use PDF and when do I use CDF, right? Notice the red and the blue. Well, PDF is when x equals something. CDF is when x is less than or equal to something. So go to that problem, number 3. Which one was it? Which one would we use, PDF or CDF? The one we just did. I think it was number 3. PDF, right? Because x equaled 12. Okay? So we're going to go find that PDF command, binom PDF command. So to find it, you're going to go to, clear this stuff out. You're going to go to distribution, because it's binomial distribution. Well, distribution is in blue. It's one of the blue ones right above vars. Right above vars, it's right there. So to get there, I need second distribution. Okay. The first 2 say normal distribution. We want binom PDF, right? That's what we said we wanted, binom PDF. So we're going to scroll down until I get that. Okay. Some of the calculators will go here. Some of them won't go here. Okay. So if you don't go here, you're going to put in, some of your calculators will say binom PDF, and then it'll have open parentheses. Some of them with the newer software will have this. Okay? They both mean the same thing. So if yours says parentheses open, just for a second, just pay attention for a second. So number of fixed trials. Well, for our question, it was 20, right? Probability of success, 60%. X value is the number x equals 12. Okay, so now everyone should look like this. So if yours was parentheses, actually type those numbers in. NPK. NPK. N is the first number, 20. 20 fixed trials. P is the probability of success. K is what we want it to equal, 12. Okay? So whether you have the old or the new, should say that. Okay? Then we're going to enter. And that's the number we have. That's the number we got yesterday. Okay? This comes in handy when you're doing multiple choice, because multiple choice, you're not required to show work. So if you need to find something like this and it's multiple choice, boom, just go right there. If it's free response, now this is the big one here. If it's free response, they will take off points. AP and me will take off points if we see binom PDF, binom CDF on your paper. If you actually write that down, they will take points off. Why? Because it's not statistics. It's calculator language, right? We don't want calculator language, right? So I don't want to see Binomial PDF or CDF on your paper. What do I want to see instead? This is what I want to see right here, which you already had. That's what I want to see. Okay, because that's what your calculator is doing. That's exactly what your calculator is doing. But it's just doing it a little faster. So if you use the calculator, this is what I want to see. Let me erase this real quick. That's what I want to see. What does x equal? What are the combinations? 20, choose 12. What's the probability of success? How many successes are there? What's the probability of failure? How many failures were there? That's what I want to see on your paper. Nowhere on my paper is there binomial PDF, right? That's the command we use on the calculator. We don't write that down. You don't actually write that down. Every time I see, and I will see this when we take a test, I will see people write that down, and they're like, "Oh, this is I put binomial. I use PDF, and then I used what was it, 20.6. What was the last one? 12." And then they'll say, "I got this." That's what they'll put. If it's worth 3 points, you'll get 1 for the answer. You'll lose 2. Because this is not statistics. That's calculator. That's calculator. Okay? If it was a computer science class, that would be okay. But this is a statistics class. So they don't want to see that. Okay? What they want to see is you actually plugging it into the equation, just like that, and getting an answer. However you got that answer is up to you. If you wanted to do the method we used yesterday with combinations, right? With combinations, right? Combinations, okay? That's fine with me. And then plug it in like we did yesterday, that's fine. Or if you want to use the methods we use today, that's fine too. But just no calculator language on your paper because you don't want anyone to grade it with calculator language. Okay? All right. We'll do that again. There's another problem we're going to do in a second here, and I'll talk about that too. Okay? All right. So let's go to the next problem. Let's go to the next one, number 4. So remember, this formula is given to you. This formula is given to you. This one's not. That one's not given. Okay? But that formula is given to you on your formula sheet right there. Okay? But you got to know what P is. You got to know what K is. You got to know what N is. You got to know how to use it. Okay? That's what we're working on today. All right, so here we go. Number 4. Back to genetics. Genetics says that the genes children receive from their parents are independent from one child to the next. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let X be the number of children who end up having type O blood out of the 5. Find the probability of X equaling 3, and then interpret. Okay, so we have to find this. That's what we have to find. Okay. First thing is, what is X? What does X refer to? When we use the letter X, what are we talking about? Number of children with type O blood, exactly. Okay, number of children with type O blood. Okay, so we want to know out of the 5 that were there in the family, what is the probability 3 of them are going to have that type blood? That's what we want to know. Okay, next question. Is this binomial distribution? How do we know? What tells us yes or no? There you go, bins, right? The 4 conditions. The 4 conditions we talked about yesterday. There are 4 of them, bins. The first one is binary. So is this a binary situation? And if so, what are the 2 options? Yes, whether they have typo blood or some other type of blood. So that binary check. Are each trial independent? It said, right? It actually said each trial is independent. Okay. Are there a fixed number of trials in advance? How many? 5. 5 children. Okay. And is the probability always going to be the same no matter which trial you're in? 25%. So we're good. Now we can use binomial. So we're going to use the formula. All right. So let's go here. So the formula is right above. So n. What is n for this one? 5, right? N is the number of trials, fixed number of trials. It says right there. If you didn't know, it says right there. Okay, so 5 goes on top. What goes on the bottom? 3. 3 is the question, the answer to the question equals 3. Okay, next one is probability. Probability of success is 0.25. K, how many successes am I going to have? 3. Okay, last one is failure. What's the probability of failure? So 1 minus success. So what is that going to be? 0.75. If I have 3 successes, how many failures am I going to have? 2. That's all the work I need to see. From here, use your calculator. You can use the method we used yesterday with combinations, or you can go to Binomial PDF or CDF. Doesn't matter to me. I would probably use one of these 2 guys. So is this one going to be a PDF or a CDF? Because it's equal, right? It's equal to 3. Okay. So let's go to your calculator. How we got 2? Because n minus k, what's n? Okay. What's k? What's 5 minus 3? So we got 2. I just did it in my head instead of writing them both down. Okay, so here we go. All right, so let's go back here. Okay, so watch and then do. So if you're like, I got this, then go for it. But if you're still, I only did it once, so you're still learning. So watch and then do your own. Okay, so the first thing I'm going to do is I'm going to go look for binomial distribution. It's distribution, so it's under distribution, right under vars, or on top of vars, I should say. So second vars. Okay, so do that if you haven't already. Okay, now I'm going to go find the one that I want. PDF. I want PDF. Binomial PDF. Be careful. There's a lot of PDFs. Number 1 is a PDF. Number 5 is a PDF. 7 is a PDF. 9 is a PDF. Just be careful because we want the one that says binomial PDF. That's letter A. So if you're given binomial parentheses, N comes first, P comes second, K comes last, close parentheses. Okay? If you're given one of these guys, then you just fill it out. You just fill out there's 5.25, 0.25. What was K? 3. N, comma, P, comma, K. Enter. That's our probability. So that's the number we're going to write down. We're going to go 3 spaces. 0.088. Oops. Okay. Okay. Now we have to make sense of that number. The probability of 3 children having type O blood is 0.088. That's it. Okay. So now number 5. Read number 5. Number 5 is almost similar, or almost the same, I should say, identical. What's different about number 5? Is it the same question, or is it the same type of question? Okay, so what is it asking? You're right, it is asking something different. No.
Will more than 3 kids have type?
Okay. So it's asking, so how would I write that out? How would I write that out? They're looking for the probability x is greater than 3. More than 3, right? More than 3 means 4, 5, 6, 7, 8, 9, right? Doesn't include 3. If it's at least 3, then they would include 3. So it's going to be greater than 3. Well, we're going to ask that question. We're going to figure that out. So, how do we do this? We can do it on the calculator. What are we looking for here? What am I looking for here? Okay, but yeah. There you go. I'm looking for the probability of more than 3. Well, how high do I go? So if it's more than 3, what is it going to be? 4 and, so what I'm looking for is this. That's what I'm looking for, right? Right, which Taylor said. Okay. Individually, can I do each of those? So it's just two PDFs combined, right? You do PDF for 4 and you do PDF for 5. That's it. That's the only work I need to see. That's the only work I need to see. This tells me exactly what you're doing. You're finding PDF for 4 and you're finding PDF for 5, and you're adding them together. So the rest is just you just crunch the calculator. Okay. So you're going to do a PDF for 4 and you're going to do a PDF for 5. So let me get the calculator back out. I'm doing a PDF for 4. Well, the PDF for 4, n is the fixed number. That's still 5. Probability of success is still 0.23. X value is not going to be 3 now. It's going to be 4 this time. N, comma, P, comma, K. N, fixed number. P, probability of success. K is the number you're looking for. Hit enter. I'm going to write that down. 0.015. Now I'm going to do that again, but instead of k being 4, k is going to be 5 now. So I'm going to go back, second, distribution, five, 0.25, now I need 5. What's the probability that all 5 kids were type O blood? What does this mean? What does any of this mean? Scientific notation, yeah. This means scientific notation here, okay? Scientific notation means the number is either so big, they didn't want to write it out, or so small, it had a lot of zeros, okay? So what this means is e to the negative 4. So your decibel's here right now. Your decibel's right in the middle, right in between 9 and 7, right? E to the negative 4. Which way are the negatives, left or right? Left. So I'm going to move my decimal left 4 times. 1, 2, 3, 4. How many zeros am I going to have? 3 zeros. You're going to have 3 zeros. So it's going to be 0.00098, we'll say. That's a small number. Yeah, scientific notation we use for either really, 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 really big numbers or really, 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 really small numbers. No. No, yeah. Okay. So now we're going to add those two up. Yep. We're going to add up the last one plus the one right before that. I guess it's just 5. That was it. 0.01598. What's that? This is what I got for each of them. I went 3 spaces on 4, x equals 4. I had to go more because if I only went 3 spaces, there'd be a lot of zeros. So I had to go a little farther for that. So is there a good chance or a not so good chance that this would happen? Not so good, right? There's about a 1 or 2% chance that 4 or 5 of the kids are going to be type O blood. All right? There's a better chance that only 3 of them would be type O blood than those 2 combined. Okay? Let me ask you this question. How many kids would you expect to have type O blood? Just one? So about what? About just, if it's a decimal, about what? About how many kids would I expect to have type O blood in this family? How would we figure that out? It's actually easier than you think. There's 5 kids, 25% chance that they have type O blood. How many would I expect out of those 5? How'd you get that number? There you go. Easy as that, right? Multiply the total times the probability. 1.25, so around 1 or 2. I'd expect around 1 or 2. That's why this number is so small. 4 and 5 is very, very small because we're not expecting that. There's a very low expectation that there's going to be 3, 4, or 5. Okay? Okay, so let's see here. Let's do this one. Let me ask you this question. No, let's do this one. Let's do this one instead. Number 6. Let's do number 6. So here are the steps we just did. The steps we just did. I just put it there straight from your book. But it's the steps we just did on the last 2 problems, on number 3 and number 4, and number 5. Okay? It's the steps we're going to use. So number 6. The top of the page is the calculator directions, but number 6. A local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the card chosen is a 3, the customer's order is free. Otherwise, the customer has to pay their regular, whatever it was going to cost. Okay? So again, one more time. You go in and get a lunch. You go in and get a lunch, wherever your lunch, whatever place you go to lunch. You place your order. Before you pay, they have a little touch screen. You hit the touch screen. It simulates a random deck, a card being pulled from a deck of cards. If that has a 3 on it, free lunch. If it has anything else, you got to pay. That's the promotion. Okay? So on the first day of the promotion, 250 customers place lunch orders. Find the probability that fewer than 10 of them will win a free lunch. Okay, so the first thing we got to do is write out what we're trying to find. Actually, before we do that, is it binomial distribution? Is this binomial distribution? Binary. What are the 2 options? You get a free lunch or you don't, right? You either get a free lunch or you pay. Okay? Independent. If I were to go in and I lose, the person behind me, is that going to affect their chances of getting a free lunch?
No.
Why not?
Because technically the card is going back in the deck.
Yeah, you're redoing it, right? It simulates a full deck. So it's not like they pull, it simulates a full deck. So it's independent. Good. What's the next one? Fixed number of trials. Is there a fixed number of trials here? 200. 200 people. A lot of people. Okay. Is the probability of success the same for all 200? Yes, because it goes with independence, right? What is that probability? We didn't talk about that. What is the probability that a person wins? Just one. There's how many 3s in the deck? 4, right? There's one of each suit, right? 2 reds and 2 blacks out of 52. Okay. Okay, so it is binomial. All right, so now let's write down this in terms of P, probability. So what we're trying to find is this. The probability X is what? Less than 10. Fewer than 10 means less than 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Do we count 10? No, fewer than 10 means less than 10. Okay. So who are we trying to find probability of? What are like we did here? Like we did on the one right before? It's kind of like that one, except greater than instead less than, right? So we listed the numbers that were greater than 3. What are the possibilities less than 10? Let's start with the first one. What's the first one? Is 0 a possibility? 0 people get free lunches, yeah. So 0. Then I'm going to add that with, what's the next one? Probability of 1 person getting it. Now, it's a long list, right? And you're doing the same type of stuff. We've done this before. If you're making a list and it's all around the same stuff, you can use this notation. It says, I'm going to continue doing the same thing I've been doing. 0, 1, 2, 3, 4, 5. And then you finish with your last one. Who's the last one? 9. That's all the work I need to see. That's all the work I need to see. Okay? Even using a calculator. This is going to take some time, right? Because I got to do 9 different things. I wish there was a way it'd be faster. And there is a way it's faster. CDF. That's what CDF is. CDF does everything less than or less than or equal to that number. Okay? That's when we use CDF. If I want to do a long list of things very quickly using binomial distribution, I'm going to use them. I'm going to use CDF, right? So this is what I'm going to use CDF. Okay, so be careful with this one though, because sometimes it gets a little confusing. Okay, let me go to my calculator. Distribution, binom CDF, fixed number of trials. How many trials are there? 250. Probability of success, what did we say? 4 out of 52. 4 divided by 52. Okay. X value. What number are we going to put in here? This is where it gets a little tricky with the X value. What number am I going to put here? Before we do that, CDF always starts with 0. CDF starts with 0. Okay, I didn't put that on here. I should put that on here. Binom, no, not even binom, it's just CDF. CDF starts with the probability x equals 0. It starts with the probability x equals 0. And then it goes the probability of 0, the probability plus 1, the probability, not plus 1, the probability x equals 1, probability x equals 2, probability x equals 3. It goes until we want it to stop. So my question is, when do we want it to stop? So if I put 9 in there, so if I put 9 here, it's going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's your answer. Is that what we want? So one more time. If we put 9 in there, so let me put 9. I'm not going to hit enter yet, but I'm going to hit 9. If we put 9 in there, that means we want to find the probability of 0, the probability of 1, the probability of 2, the probability of 3, probability of 4, all the way to the probability of 9. Is that what we want? Is that what we want? No, so I want each individual, and I want them to add it all up. That's what it'll do. That's what CDF will do. CDF will find the individual, and then it'll add it all up for us. CDF stands for cumulative. Cumulative means it'll add it all up for us, which is nice. So do we want it to start with 0 and then go to 1, 2, 3, 4, 5, 6, 7 and stop at 9? Is that what we want? Okay, if that's what we want, hit enter. If that's not what we want, choose something else. Okay? And there's your probability. Make sure this did it right. I'm not sure. I've never used fractions in here, so let me double check something real quick. What is 452? 4 divided by 52. Yep, same number. Okay. So the probability that fewer than 10 people win on that day. That's the probability that fewer than 10 people win in that day. Okay, not very many. I want you to do this now. Give me the probability that more, less than or equal to, no, let's do a bigger number. Let's do 85. I want you to give me, what's the probability that at least 85 people win a free lunch on that day? At least 85 people win a free lunch. At least 85. At least 85. At least 85. At least 85. So when I say at least 85, what does that mean? 85 and higher, right? So we start with 85, 86, 87, and then when do I stop? Okay, so that's what we're trying to do, right? So, all right, go to my calculator. So is this a binomial, CDF, or PDF? CDF, okay. Still 250 trials? Probability of success still the same? Okay. What's the X value? 85? Or what do you think? 250? How many of you did that? Okay. 100% chance. We're going to have to do some subtracting, right? When I put 250 here, Where did that start? Where does CDF start with? No, where does CDF start with? Thank you. Someone read the notes. CDF starts with 0. So what the calculator did was say, wow, you're not very bright, Mr. Flores, because you want to know the probability of 0, 1, 2, 3, 4, 5, 6, all the way to 250. Isn't that everybody? Right? Sure, it's 100% chance, right? That's everything. I don't want that, right? I want to take that and I want to take away a piece, right? Don't I want to take away a piece of that? So I want to go 1 minus what? Who do I not want to count in this? Okay, so how do I write that? Probability of how do I write that? What you just said. No. How do I write that? Less than or equal to 84. That's what I want. Okay, that's what I want. So the question is, how do I find this? Okay, so what do we put in? So I'm going to go back. PDF or CDF? Okay. Fixed trials. How many fixed trials? 250. Okay. Enter. Is probability still the same? Okay. What's my X value? Okay. That means I'm going to start with 0 and I'm going to go up to 84. Is that what I want? I'm going to start with 0 and I'm going to go up to 84. Is that what this means? Yeah, that's what it means. Yeah. What did I get? What did I do? Oh, I know why. Because the probability is so high that my calculator is just rounding it to 1. Let me see if there's a way to change the mode here so I can. What's happening is it's not 1. The first one was 1. When I said 250 out of 250, that's 1. But this has such a high, it's 0.999999999 something that my calculator's like, you know what? I'm not going to write all those 9s. I'm just going to put a 1. There's a way to change it, but so what's happening is darn near 1. So this number here is pretty much 1. So what's the probability of more than 85 people winning? Pretty much 0. Pretty much 0. Pretty much 0. Squiggly line means approximately, pretty much. Pretty much 0. Does that make sense in terms of the problem? Why? Why does it make sense? How many people would I expect to win free lunch? Around how many? Around 19, right? 19 is about 7-8% of 250. This is asking for more than 85. there's very small chance that that's actually going to happen. That's why the number is pretty much zero. The chances that the number of people who wins is somewhere between 0 and 84 is almost a whole, one whole. Okay? So that it makes sense. Okay, so in fact, only 9 customers want a free lunch. Does this result giving convincing evidence that the computer program is flawed? How many would we expect to see? How many on a given day, how many people out of 250 would we expect to win a free lunch? 19, 19, 20, we said 19 point something. Okay? Only 9 people won. Only 9 people won that day. Is this convincing evidence that something is wrong with the computer? How would we answer that question? Either yes or no, but how would we back it up? How would we justify it? So we would say the expected value is 19 or 20. Do we know how many? Do we know what the chances are that 9 people would win? We can find out, right? So let's do that. What's the probability that what happened happened? What's the probability that what happened was 9 people won? $250. 4 out of 52. We're looking for 9. 004. I don't know, Julia. Okay. All right. Is that a big probability or a small probability? So my question is, does that provide convincing evidence that something is up?
Yeah, because there was a very small chance that this should have happened, but it happened.
So
So the computer is flawed.
it has to be, right? If there's only that percent chance, this not percent, this is less than a percent. If there's this probability that what you're saying happened actually happened, something has to be wrong with the computer. Something has to be wrong with the computer because the chances of that happening are so small that it should not have happened. It should not have happened, right? Because of that, yes, there is convincing evidence that something is wrong with the computer. Okay? So again, if this is a 3-point question, you get 1 point for saying yes. You get 2 points for justifying your yes. Yes. Since the probability of x equal 9 is 0.004, this event should not have taken place. If machine was not flawed. Shouldn't have happened. That probability is so small. Like if there's a 0.004 probability it's going to rain today, and it rains today, you're gonna say, well, whoever predicted this must not know how to do their job because they didn't know, right? It's the same thing. It's the same thing. If something has that small chance of happening and it actually happens, something went wrong. Something went wrong. Okay? Our calculations weren't wrong, so that means the program had to be flawed. Okay. Now, if the number's big enough, if they say there's a 25% chance it's going to rain and it rains, you're like, it's not that bad. But that's less than 1%. There was a less than 1% chance it would happen, and it actually did happen. Then something's got to be wrong. Something's got to be off. Okay? All right. Okay. We will. See, we've got a few things more to do. We're almost done with this, actually. Because then we go to geometric. I might let you start on an assignment, so practice an assignment tomorrow. So you guys can do some practice on your own.